All right, in this video we're going to talk about Ka and Kb. We're going to be talking about the equilibrium constant for acids and equilibrium constant for bases. So let's talk here first about strong acids versus weak acids. Okay, let's say this is a generic equation for an acid. Remember, H on the front, compared to a weak acid. So here's the deal: when this guy is put into water, it dissociates or breaks up, and you're going to get these and these made. Now, instead of writing a hydronium, I'm just going to split that into positive ions and negative ions. This is what makes an acid so strong, right? Okay, here's the deal. If it's a strong acid, it goes 100% that direction. As soon as you drop this in water, all you have is ions. There's no molecular form anymore. On a weak acid, it's the opposite. H plus A minus, it's going to really hang out over here in molecular form. Very few. It's a small percentage. 1, 2, 5% of these molecules go that direction. Some do. Okay, so think about it like this. If I put equal amount of this, I'm going to use simple numbers. If I put 20 molecules of this into water, all 20. So I'm going to get 20 of this and 20 of this floating around. Great. But if I throw 20 of this in there, I may have 2 that broke up and 18 are still in that form. When is the acid effective? Only when you have hydrogen ions. And so they have less than 100% dissociation. So you'll notice in this example, these are fake numbers, but it's going to stay really in the molecular form. It's not going to try to break up into the ions. So it's a very, very weak acid. That's why citric acid, okay, is one of those that we eat. Salicylic acid, which is found in aspirin, is a weak acid. How do I know? We don't eat strong acids because it would burn up our mouth. Now, in our stomach, hydrochloric acid is a very strong acid. It breaks down our food. That's why people that have eating disorders are going to have very bad teeth. If a person has throwing up disorder or anything like that, they throw up so much they're washing this really strong acid over their teeth, it's going to eat away at the enamel of the teeth. They're going to have horrible teeth. But if you eat lemons and you eat sour candy and you eat oranges and any apples that have citric acid, it's not going to do that because it's got such a weak acid. Most of it's in this form. It doesn't have very much of this that eats away. Okay, so it's really interesting. It's very important to understand that it is breaking down, but it's just not breaking down enough. Okay, so let's talk about the Ka value. So the same thing works for bases. Okay, you have strong bases versus a weak base. So I'll just show this to you real quick. Strong base versus a weak base. Basically, a base is going to add the water. And remember from Bronsted-Lowry, it's going to be a proton acceptor. So the H is going to come off of here, one of them, and it's going to attach to here. And you're going to have an OH that's left. In a strong base, it's going to go really far this way. There's the base property. Do you see it? OH minus. For a weak base, when you have that weak base, and you put it into water, it's really going to stay this form. A little of it does this, but you just don't have enough made for it to be strong enough. Okay, so it's the same reasoning. The particles are different. An H compared to an OH. Okay, so let's talk about Ka. Let's take that equation that we had a while ago, Ha plus water. Okay, so we're going to drop it in water. Why? Because it's aqueous. We're going to get H3O plus this. Okay, so what is happening from here to here? Okay, we were doing Bronsted-Lowry. Remember this? The H is donating. So this is definitely an acid, Bronsted-Lowry acid. This is going to accept it, which it's going to act like a Bronsted-Lowry base. We've already done all that. That's fine. Okay, but let's take it to the next step. If I wanted to have the Kc for this reaction, remember Kc, it's products over reactants. Here it is. There's my products over my reactants. All right, that's exactly right. Now, in one of the other videos, we've already said this, but I'll say it again. Every acid is already mixed in water. You have to make it aqueous. So this is dissolved in water, this is dissolved in water. Is water part of the reaction? Okay, there's water everywhere. Okay, it's going to be this way in acids and bases and other solutions. There's water everywhere. And so here's the deal. In molecular form, we're just going to ignore it. So in reality, your Ka for your acid is going to be hydronium and the end of the acid over your concentration of your original acid. Okay? Now here's what that means. If you were plugging in to your equation, okay, if you were plugging numbers in here, okay, this is going to be a strong acid if your largest number is here. If this times this is bigger than this number, that's a strong acid. It's a weak acid if this is your largest number, which that makes sense. Why? From before I erased, we said this goes 100% that direction is a strong acid, so you're going to have total ion dissociation, so those numbers are going to be your biggest numbers. In a weak acid, it's staying this direction, which means that number is going to be highest, so it's on the bottom of the fraction. Okay? So you're going to do the same math that we've done before. You would multiply molarity times molarity divided by molarity. But what's basically going to happen, said a little bit different, if your Ka is greater than 1, which means the top number is bigger, it's going to be a strong acid. If your Ka is less than 1, it's a weak acid. Okay? Now, here's where we start plugging in things that look really crazy. There is what is called the pKa. Well, the first thing that makes me think of is pH. How do we do pH? You take your H concentration and it was what? The negative log of your H concentration. So if this was pH, it would be negative log of the H concentration, but since it's pKa, it's the negative log of the Ka concentration. Okay? We'll use that later in this unit, but that becomes very important because we start taking numbers that look like this, 4.5 times 10 to the negative, ninth, and they end up being numbers like 4.2. We take them out of that scientific mode, and so it's going to help us with some patterns of what's going on. So this will be important later, okay? But I'm showing it to you so it looks very similar to pH. That is Ka. So notice it jumped from, we're just doing a basic equilibrium to, it was a Ka. How did I know? Because of that. Hydronium shows off as an acid. There's the end of the acid. So the H make a hydronium, they've separated. There's the acid basic formula. Okay? So let's talk about Kb. If I had a base, so we'll use the formula we had a while ago. There it is. So you have a base. Remember, Bronsted-Lowry says bases are proton acceptors. So an H is going to go from here to here. I can see it. Now it doesn't matter if I wrote BH or HB, it doesn't matter. And there's what's left of my water. So if I do what I've done before, Kc is equal to your products. Products over your reactants. And from what we said in the last one's true here, we ignore the water, okay? Because everything's going to be in water as we go along. So your Kb, now how do I know it's a Kb from a Kc? It's Kb because this is a base. Now we would use real base formulas, but because it's a base, we already talked about that. Look, it's making OH, it's acting the base. Kb is going to be this hydroxide over concentration of your original base. And the exact same thing is true. It's a strong base. This is your largest number. It's a weak base if that's your largest number. Okay? So works the same way. If your Kb is greater than 1, so that means their top number is bigger. Strong acid, or excuse me, strong base. If your Kb is less than 1, it's going to be a weak base. Okay? So it looks very, very similar. So when you start seeing your KB numbers, if your KB numbers are so when you plug numbers in, or Ka or Kb, if they're greater than 1, you know it's automatically strong acid or base. If it's less than 1, it's going to be a weak acid or base. Okay? Now, if you want to reference that in your book, page 483 is where you can see all that derivation. Okay? That's where you can see all that derivation as you go along. Okay? Now, when we start, and again, we're taking what we've just learned the last couple of videos and put it together. Star. If you start with a strong acid on the left, because of Bronsted-Lowry, what do you have on the other side? Well, you have a conjugate base, right? So if it's a strong acid going one way, then it's going to be a weak conjugate acid. Excuse me, I said it wrong. If it is donating an H, it's going to have to take in an H to come back. One more time, if it's donating an H, it's a Bronsted-Lowry acid. If it's going to come back, it's going to have to be a weak conjugate base. Same thing is true here. If you have a strong base going this direction, what you're going to make on the other side is a weak conjugate acid. And it goes right with your Bronsted-Lowry definitions. So let me show you an example of that. Hydrochloric acid and water produces hydronium and chlorine ions. Now let's do Bronsted-Lowry like we did. This becomes this. What's it doing? Proton donor. Okay, so that's the acid. So if it's an acid going this direction, it's a base. Conjugate base. Coming back the other way, right? Checking myself. H2O to H3O is a base. It's a proton acceptor. So to come back the other way, it's got to be a conjugate acid. Now, don't get confused. I just happen to write it this way. Some people get stuck and say, oh, it's always acid-base, conjugate base. They can all be, it could start with a base, acid. They just happen to be acid-base, acid-base. Okay, so don't think I'm doing that purposely. It just happened to fall that way in this question. All right? So all of this falls out just like we were talking about with Bronsted-Lowry acids and bases. Go straight with what we're learning with Ka and Kb. All right? So the question is, now that we've got the formula, what's the Ka for water? All right? So what's the Ka for water? Okay? Well, the formula that we had was water basically is going to be hydrogen ion concentrations and hydroxide ion concentrations. What, do you remember the molarity that I wrote in the other video? Yeah. 1 times 10 to the negative 7th molar and 1 times 10 to the negative 7th molar. And we also found out that 55.4 molar was the concentration of just pure water, and we did that math earlier. So Ka equals your concentration of your products over your reactants. All right, so we plug our numbers in. This is 1 times 10 to the negative 7th. This is 1 times 10 to the negative 7th. Both of them are molarities over 55.4. So what's your Ka? So you grab your handy dandy calculator. 1 times 10 to the negative 7th times 1 times 10 to the negative 7th. Negative 7th. Come back. There you go. Negative 7th equals divided by 55.4. The answer is 1.8 times 10 to the negative 16th. 1.8 times 10 to the negative 16th. So your Ka. So the question becomes weak or strong? Well, look at what you wrote a while ago. If Ka is greater than 1 or Ka is less than 1. Look at that number. It's less than 1. So this is a weak acid. Okay? That is a weak acid. So this number is sort of like this little magical number. Sort of keep this off to the side somewhere. Make sure you use that, okay, because we're dealing with water. So when you reference things to water. So here's the deal. If anything that has a Ka that's much, much greater than 1.8 times 10 to the minus 6, okay? So that's going to be stronger. So acids with a Ka that's 1.8 times 10 to the negative 16th. I'm sorry, I wrote that wrong. Ionize easily in water. Why? Because if these ionize that small amount, anything that has a Ka much greater than that number, when you drop them in water, they're really going to go far to the right. They're going to break into ions. Okay? So what ends up happening for us is there is a factor that you can actually find to make your life a little easier. Okay? And there's a derivation in the book, but you don't have to know the derivation, so I'm going to go ahead and just give it to you. And that is the last thing we're going to do in this video, and here it is. Kw equals Ka times Kb. Now, where would that come from? Well, if you had pure water, okay, you can do the K value for that. Well, that's an acid, right? Acids do this, bases do this. And you can put all three formulas together and solve, and what you will find is this. And this is a super important fact. It's sort of like pH plus POH equals 14. In reality, let me show you where it matches. 14 equals pH plus POH. Acids have those kinds of pHs, right? And bases have POHs equal 14 on that scale. Well, they're all related to one another, all these different things that we've done along the way. So you're going to be using these to do some calculations. If it's a Ka, remember, you're going to do what we did on this one right here. Remember, we took your Ka was going to be your concentration of your products over your concentration of your reactants. They give you values for these. Figure out the Ka. If they give you the Ka and you don't know something, it is just algebra manipulation, and you solve for what you don't know. And so the questions themselves are not very difficult, but we build on it from this point forward. Ka, Kb, Kw.